Hi, I'm Maddie Stone, and this is the smarts behind hacking dumb devices. So basically my bio, I am currently a security engineer on the Android security team at Google, but this has nothing to do with that. Instead, it focuses on my first love before Android of hacking and attacking embedded devices. And so that's a lot of different microcontrollers and all those random architectures you see in IDA that you're like, why do they support this? M32R, etc. I love them, and please keep supporting them. So I've also am the creator of the IDA Python Embedded Toolkit. So let's dive in. So the whole purpose of this talk and why I wanted to give it is to really get into what is that whole process and mindset behind when you're attacking and trying to break non-IoT embedded devices. So what is this target device? What is dumb devices? And basically, it's everything that surrounds you on a regular basis that has a microcontroller controlling or sensing some sort of physical world aspect. So your thermostat, if it's not IoT connected, all of your electronic control units in vehicles that don't have any of the wireless connectivity, your hairdryer, your blender, they surround us all the time. And I focus specifically on these dumb embedded devices versus IoT, and I make that distinction since currently we talk a lot about embedded devices as smart or IoT because it's just a different way to attack them. We have to think about it differently. Because when you have these IoT and smart devices, a lot of the attack vectors that we look at are focusing on that Wi-Fi or Bluetooth stack, or how are they processing and sending data. And the other aspect is they're usually running Linux or a version of there or an RTOS. And so the special sauce of that one device you're looking at, if it's IoT, tends to be at the application layer. And it's working with device drivers to interact with the physical aspects in there. So when we take a step back and go to dumb embedded devices, a lot of the times they're running on bare metal or a very minimal operating system. So when we're reversing that, it's just a different problem. And I wanted to focus on this because they are everywhere and they control a lot of these really critical things that we're looking at. So they're still everywhere in our vehicles. They're everywhere in a lot of our ICS control systems that haven't been connected yet. They're also, in a lot of things that just run a motor. But they're also a really, really beautiful intersection of hardware and software. So you get to work on this hardware reversing side of things and leverage this knowledge of EE and CE, but also tie this into very directly with computer science and your knowledge of firmware reversing. And it's really fun as an attacker because when you develop that exploit or that implant for your device, you get to see something physical happening before your eyes, whether that's on purpose, you see flames, or you stop a motor, things like that. It's just really a lot of fun. So let's take a step back and talk about what do we mean when we say let's attack these dumb devices. Basically what that means is whatever you want, where you're trying to get that device to act in an unintended way. So we're going to talk about this process will apply if you just want to make your water alarm system work differently than the manufacturers intended it, or if you are really trying to red team it, a system that, a vehicle, a control system or something like that, that has a lot of bigger implications and maybe stop it from working, make it break physically so it can no longer operate. So examples of this and sort of how I break down the idea of attacking and creating unintended things to happen is one, it can be as simple as you want to exfil the data that it's communicating with. It might not have a wireless interface, but there's still a lot of wired protocols that are talking, and they might be saying a lot of interesting stuff that you want to track and know what this device is seeing or thinking. So you want to add an attack that exfils it out to yourself. Other things is you want to modify the control algorithms. So what that means is when we take a step back again into what does a embedded device do, it senses a physical environment and makes a decision to control something else physical. So we want to change that inner point of that control algorithm. So let's say we have our example of a water sensor you put in your basement to decide if it's flooding. At a certain point, when it senses moisture, it's supposed to sound an alarm to tell you your basement is flooding, and maybe it turns off your water supply. So we have a couple of different places we can look and change that control algorithm. If we are trying, as a homeowner, we want it to operate a little bit differently, so we want it to sound an alarm earlier. That might be a time that we attack it. Or we're a malicious actor or red teaming it, and we want that alarm to never sound. So that person, wherever they have that water sensor, it never goes off. So that's what we mean when we're talking about changing the control algorithms, either on the input and or the output side. The last thing is you might want to add features to it. You have this beautiful little box that has all of these peripherals associated with it. It gets to hook up to motors, it hooks up to thermostats, or other important things, some relays that go to other interesting things. And you just think, it would be great to add another feature to bolster it, or you're a homeowner and just want to allow it to interact with something else. So we can really break down this whole attack and offensive mindset and process into 4 steps. It doesn't have to be more complicated than that. The first is goal and constraint setting. We really need to know what is the whole purpose of us trying to attack this thing, and how far are we willing to go? Because it is very likely that you might destroy the thing. Is that okay? And it will help you decide which techniques to use through the whole process if you know what your constraints are. Then we go into our initial triage. Finally, the iterative analysis part tends to be the longest, and that's where all of our hardware, protocol, and firmware reverse engineering is happening. And finally, the execution. How are you attacking this? Is it a remote attack over some serial interface it has? Are you implanting firmware? Are you implanting hardware, or both? And what does that look like, and how do you build it? So let's start with our initial goal and constraint setting. What I mean when you say you need to set the goal is take a step back from the technical mindset. What are you interested in? Are you interested in making this device stop? Are you interested, like in our water example, of changing the behavior? Making sure, communicate with it, all those different things. Make sure you know so you can always focus all of your reverse engineering and efforts just on the pieces that will apply to help you reach that goal. What do you need to access to accomplish that goal now? Are you going to need the circuit diagram, the net list of how all those pieces on your printed circuit board inside the device work? Are you going to need to know the pinouts if it has a connector to something else in the the outside world? Do you need the firmware? Do you need the comms traffic going to and from it to understand it? Is this device one piece of a larger system? And are you going to have to somehow find a way to instrument it in that larger piece? One other thing that I forgot to mention is where this comes in handy is in a lot of our IoT and larger systems, we have dumb embedded devices. It's very rare nowadays that you open up a connected system and there's only one CPU. A lot of times they have other microcontrollers or such as their driver chips or controller chips or other things inside that board as well. So your device at that point might be that subset in a larger system. I can't see. The next is how destructive can you be? Do you have one copy that must work at the end? That's going to change your techniques and your approach. Change it a lot from if you have a lot. It's a $40 device. You don't mind going out to Walmart or whatever store in your part of the world has a lot of different things and can go. Are you worried about anti-tamper? That might be in there, and that if you open it up, it's gone, it's done. So just framing out what your attack is going to look like to help inform you as you continue on through the process. And lastly, how many resources are you willing to apply for this project? Because it's really, really easy to get trapped down a rabbit hole of, I'm going to decap this chip and remove this chip and all of these other really exciting and fun and sparkly techniques, but it doesn't fit what you're actually willing to do and what your goal is. But then we can get into fun, right? But first we gotta pause. So my biggest thing that I would like to emphasize is if you want to do this, make sure you capture the behavior and traffic before you start changing or tearing apart the device. Because these are things such as, what is the timing between each message that it sends out? Or how long does it take to respond from if it has a switch You pressing that switch and it actually responding on the physical end. Because otherwise you're going to get to your end point when you're analyzing, you're debugging, you're interacting with the system, and you're not going to be able to tell, did I cause that to happen, or is that normal? And so that's where it's really important, and it's really, really hard because we all want to be impatient and dive in to make sure you capture all of these important things. What does the message look like? What are the voltages that it's sending things out? All those different combinations. Then we have the open source review. I wrote programming methods. What I meant is a lot of chip manufacturers put out programming notes to suggest to you, hey, if you want to connect this I2C thing to our chip, we suggest you just do it this way. Those are goldmine. Use them. They're awesome. And then we can actually tear it apart. And the first thing here in initial triage is let's identify all of our components. So the main things that I always look for when I tear this apart to get the first idea of how long this is going to take is what CPU is in there, and is external memory, hopefully, or I tend to like it when it's external memory, where the firmware is stored, and also does it have any non-volatile memory as well that is separate from the firmware. And so identifying those chips, starting to see, okay, is there power, is there RF, just doing that basic component identification of understanding what does my board look like. Are there any hidden interfaces? Do you have debugging? Do you have comms? Do you have test points that can help you later on as you're doing this iterative process? And what does access to power look like? If you were to build a hardware implant, do you actually have access to the power that you need? Hopefully after a regulator at either, usually we want 5 volts or 3.3. So how easy, if that's the decision you want to go down, can you access that? And another one that's not listed is how many layers does it look like the board is? And we'll get into that. The next really crucial piece in this initial triage is trying to, or at least setting out a plan of how do you obtain and access the firmware. There's a lot of different ways to access the firmware, and this is going to inform your implant. It's going to be one of the largest determining factors of how do you build this implant or attack that you're looking at. So you will find so many wonderful, wonderful talks really getting into details of different types of firmware extraction methods. Some are on the software end of the spectrum, such as, is there a board support package that gives me access to downloading all the memory? Is there a serial console? Can I write in a patch because I have debugging to read it out, even if it's bit by bit? Is it on the internet? It's a great one. So looking for any sort of debugging interfaces like JTAG, in-circuit emulation, debugging. Maybe you're gung-ho for just removing that chip and putting it in a chip reader. You get ground truth, it's great, things like that. And maybe you are really have a lot of resources at your disposal, and you are playing a highly sophisticated adversary, and you're going to decap the chip and use a scanning electron microscope to look at the transistors inside of the chip and read out the memory. So really just focusing and coming up with a plan of how do you want to obtain and access the firmware, and if it's possible. The last piece to start thinking about is, are you going to need to instrument this device? Does it need to run in that larger system? Do you need to create something that's going to talk to it to be able to have it operate in the way expected? So this is where huge decision points happen, and they can really help make you more efficient from here on. So the first one of those is, can I answer yes to both of these questions, which are, can I access the firmware, and is the firmware writable? So these two questions will be answered also by those constraints you set earlier. Maybe you can access the firmware, you can pull it off on a chip, great, awesome. But based on your use case scenario and how you want to attack this, is the firmware chip writable? So is there write enable pin connected, or can you connect to it to change it and be able to write to that chip? Are you willing to replace the whole chip to put in a new one with new firmware? Is it able to just hook up and do JTAG and be able to update it? Or do they have new security mechanisms in place that will prevent you from being able to write to it at all? And there's even cases where I've seen people change out the CPU, create a new footprint. So that's where you make up your constraints. If you have to answer no to either of these two questions, then it makes it highly unlikely that you should pursue any sort of firmware implant as your attack execution method, because you're just not going to have the time or the resources to go down that road. The next one you need to ask yourself is one we sort of talked about before, is power accessible for if I'm thinking in terms of hardware implants, and are the critical vias or traces accessible to me? So if I have a board that is 5 or 6 layers, and most of my traces and vias are on those inner layers, then it is not going to be easy for me to attach to different points to influence the operation there, because they're hidden from me. All I see are the top and the bottom layers, and I can't just put my little hardware implant on top. So these are questions you ask yourself, and if you answer no to either of these for what you need, then the answer is probably you shouldn't pursue a hardware implant. So now we got to decide, we have a lot of information, we haven't done our RE yet, but how do we want to achieve our attack? We have enough information to start thinking about that. So going back to our goal of what we want to accomplish, we see more, we know a little bit more of the system. What is that physical hardware we want to affect or alter? So in the sort of example case I gave you, there was a moisture sensor on one end and a siren on the other that tells you when you have too much water in your basement. So that means that I can really focus my analysis that I want to affect and alter either how the moisture sensor operates and or how the siren operates. There might be so many other things on the board, but that's where I just need to focus my reverse engineering, because that's what I care about. And so then I use that same information going into the firmware reversing. When I'm looking at it, I really just want to find those control algorithms that are going to process that information coming in from the moisture sensor and control and tell that siren when to go out. I don't need to worry about everything else in that block. Once I find those are my starting points, and I don't need to start at just the reset address when looking at the firmware. I might also say, though, that I care about this error control method. So that's what I mean by identifying how you want to achieve the attack. You also might want to think about, do you plan to have persistence? Because on these embedded devices, if they want to do anything persistently, they usually have to have some sort of serial chip to help them do that. So double EEPROM, maybe connected to like SPI, I2C bus. And if you want to be able to maintain that siren, say, going off all the time after it was triggered once, then you might need to set a bit and be able to read it from there. Also, your communications buses, what do you want, what do you need, what exists in this system, and any debugging interfaces, because they make life a whole lot easier. Or they can make it easier for someone to detect your implant. So now we get into the RE, my favorite. So I sort of broken down some of these key techniques into hardware, firmware, and protocol. And what's really cool and what you'll find is that they really can be broken down into very simple and basic blocks. So starting with hardware, continuity testing, you just need a multimeter. And what continuity testing is, if you don't know, is you are taking the 2 probes of your multimeter, putting them on 2 points, and the multimeter is measuring the resistance between the 2 points. If it's below its threshold, it beeps to tell you they are connected. And so you can start to figure out your board and what's connected to that moisture sensor and what's connected to the end of that siren by doing that. And why do we care? So the key point that we want to find out when doing this continuity testing is that we know our CPU, it has a signal coming into it telling it when the moisture sensor, what the value of that moisture sensor is. It's probably going to be analog to digital converter, something like that. But we don't know what pin it is. And when we look at our firmware, all we probably see is a special function register or analog to digital converter 3. And it's reading that value and doing some processing on it. So we want to connect our 2 hardware and software pieces together. So we want to use continuity testing to find out this sensor comes in through this circuitry to this pin on the board. Now I can open up IDA or whatever disassembler, radar, whatever you want to look at, and find out who is the control algorithm controlling that pin that's connected to on the CPU. So let's say that you're a software person and hardware has always been sort of a fear. You didn't want to get into it, didn't know about it. You just need a multimeter and connect the dots. Let's say you're a hardware person and you've never liked the blob of bytes and binaries and instructions that open it up. You don't need to go through everything. You just need to find those, start with your general purpose input-outputs in your firmware image, your peripheral devices, which might be like an analog to digital converter, a compare-capture, things like that. Your special function registers telling you how to operate. And then once you get there, you're really going to, so those will cover a lot of your, control algorithms. And the last piece that you probably really want to find and you're going to need is checksum validation code of when the firmware starts up, things like that, or any error checking code that it has of making sure inputs and outputs match what you're looking at. And that's really how you can break down the whole firmware reversing point of it into very manageable chunks. Other things that can really help is for, on the hardware side, dynamic probing, using your oscope to actually watch signals in process. If you get lost, those signals are on the inner board, you can't do continuity testing. Watch where the CPU pins and how they're operating and see if any of them match the behavior you're expecting for that signal you're looking for. You can also use a logic analyzer as a debugger if you literally have no other options. If the memory is on an external chip, hook up your logic analyzer to monitor the address lines that are going between them, and that can give you some sort of trace routing to know what branches in your firmware it's executing. Really, really fancy debugging, right? Yeah, and so on protocol, you can tap it. There's things like the Beagle, the aardvark for injecting into SPI and I2C, and things like that. So finally, we have a lot of information. We think we're ready. We want to develop, patch, implant, exploit, whatever you want to call it. So hardware that focuses on a lot of, do you have the space? What are your attachment points? Are there any heating constraints or vibration constraints you have to worry about and things like that? And power. Are you going to be pulling too much power from the device that it's not going to be able to operate effectively? Could it be as easy, instead of actually putting in a larger implant, can you just replace one or two components and connect traces in a different way that can achieve the same goal as you were setting up? When you're thinking about firmware, there's a lot of different ways to actually write it. And it's going to depend on what architecture you're looking at. How good are you at setting up different tool chains? How much do you have to write it? How much space is there inside the existing firmware image for you to hook into or write over? So my personal preference is, because there is generally not a lot of space in these things, is to write the opcodes, because you're a lot of times looking at, most 20 instructions to add in. But if you don't have that space, there are hooking mechanisms that people have put out there which generally take the look of, from here, save off these registers, jump to this place that has a little more space, run my code, reset the registers, and jump back. And you'll find that for different assemblies and architectures to just give you that space that you might need to write it out. But if you're running a maybe more common architecture, you're really, really great at setting up tool chains, unlike myself, you can also compile it in C, input it, get the instructions, run it. So then if you are looking at protocol, you are crafting specific comms messages, you're finding ways to input them, how can you stop it, not mess up timing, make sure it keeps running. And the last piece is that I've never had it work on the first try personally, and when you are on these limited devices and micros that don't have a lot of debugging capabilities, one of the things is you just got to get creative. So thinking about, how would I just toggle this GPIO pin to tell myself I made it to this point, or use the, is this bit set or is this bit clear, and give me some sort of physical mechanism to tell me what is happening inside this firmware, since I can't see anything else. So it's just a really fun, beautiful, creative process of merging all of this hardware and firmware aspects together. And oh yeah, on the firmware implant, make sure you mitigate checksum, because yeah, it won't work. And most of them have very basic XORs or matching to sums to 0 for different portions of it. So that is usually the last piece of making sure you find that, mitigate that in some way, whether it's jumping over the code in general, just setting it to always be successful, etc. And I think that was a whirlwind 25 minutes. I have 30 seconds left of the mindset, the process of attacking and modifying dumb devices. I obviously would love to talk more about this, get into more details, so come find me. And are there any questions?
Okay.